All right. So I think we can get started with the top portion of the seminar. So today it's my great pleasure to invite Greg here as our speaker. Greg is an assistant professor of computer science at George Mason University, where he runs the RAIL group and is the director of the GMU Autonomous Robotics Lab. His research at the intersection of robotics, planning, and machine learning is centered around developing representations for planning and learning that allow robots to better understand the impact of their actions so that they may plan quickly, intelligently, and reliably in a dynamic and uncertain world. Before joining George Mason University, he received his PhD in 2020 from MIT ECS, and actually was at Cornell. So previously graduated summa cum laude from Cornell with a BS in Applied and Engineering Physics. His work was also a finalist for Best Paper at 2018 Choral, at which he was additionally awarded a Best Oral Presentation. So with that, Greg, please take it away.
Yeah, great. Thanks so much. And it's good to be back in Ithaca despite the cold. Indeed, I have a little bit of a cough. My asthma's been acting up, but I promise it's not contagious. But yeah, so I'm here to talk about, well, I couldn't prune my title as effectively as I probably should have. There's a lot of buzzwords here and I have a lot of stuff to cover. But I think that summary really does sum up the sorts of things that I'm interested in. I'm interested in robotics, robot planning and decision making, and in particular, how to make learning helpful for making good decisions, even when the robot doesn't know very much about the world around it. So I'm generally interested in this broad vision that maybe many of you share, is this idea that robots will be expected to complete, move the mouse out of the way, yes, to complete complex objectives in homes, buildings, hospitals, etc. So something like a basic task like load these objects into a cabinet, all the way to the more complex and potentially even open-ended tasks, things that include preparing breakfast, or the maybe slightly more complicated, make the bed and restock the shelves and then bring breakfast, etc. So there are complex multi-stage objectives that require the robot to interact with many different entities in the world in order to complete this objective. Now, there are a number of different ways that we can think about specifying sub-objectives. Everything from something like linear temporal logic to PDDL, the planning domain definition language, which can be used to specify such tasks. So the robot over here on the left is given what we might think of as the natural language command, load these objects into the cabinet, but the robot is actually given a specification. So some code that tells it what objects exist, where they are, how they can be interacted with, so that the planner then returns something like, make sure that the red block is at the cabinet, red block number 2 is at the cabinet, all the way down to blue block number 2 being in the cabinet. So we can then plan in order to accomplish this objective for the robot moving to the table, picking up the blue block, moving to the cabinet, putting it down, and so on until this specification, this goal condition is met. However, robots are going to generally be expected to complete these complex objectives under uncertainty. In general, the robot may not have a map of its surroundings, and it must search for task-relevant objects in order to be able to complete even the simplest of objectives. However, most classical approaches to task planning, including the aforementioned PDDL-based planning specification language, and things like linear temporal logic, typically assume full knowledge of the environment. And so as soon as any piece of the world is not known to the robot, as soon as something they may need is not in their immediate vicinity or that they are told where it is, the robot can no longer complete any of its objectives. As a result, these seemingly simple tasks, at least maybe to us as humans with our human intuition for how to complete tasks that we do probably every day, things like prepare breakfast or even the more enumerated make the bed, restock the shelves, then find a nurse, becomes very difficult when I don't know where the bed is, or even if I know where the bed is, I don't know where the sheets are that I will need in order to be able to make the bed. So it becomes very difficult. And just to motivate this a little bit further, I'm going to talk about something that you do all the time, something that you did to get to this room, is point goal navigation, get from point A to point B. Even point goal navigation can become incredibly challenging in unmapped spaces when the robot does not have a map of the environment. So I'm going to give you this example that I've been using since I was a PhD student in the context of goal-directed navigation. I have some robot. This is a picture taken off of a ground-based robot navigating through a university building, something like this one, and it's told to get to a goal that's about 100 meters in that direction. So what do? Well, if the map is known, the navigation problem is relatively simple. The robot goes down the hall and makes an early left turn and enters the goal. The challenge here, however, is that what the robot actually sees is this. It's but a partial map of its surroundings. It can only see this white region here and the black obstacles at its boundary. Unfortunately, because the robot doesn't know what lies in unseen space, it makes an early left turn into what you probably recognize as a classroom. And so here's a video of a robot executing this simple, what I refer to as optimistic planning policy. The robot optimistically assumes that all unseen space is unoccupied because it doesn't know any better. And it makes an early left turn to this classroom and has to navigate around for a little while before realizing it's a dead end and then leaving, going back to the hallway before eventually making further progress to the goal. The challenge here is that this optimistic planning strategy, which is pervasive because of its simplicity, begets suboptimal plans. This optimistic agent unnecessarily explores many classrooms, offices, and closets along the way to the goal because it's trying to find a route around the hallway. Now, we know better than this, right? You have an intuition, and not just an intuition, you have experience in environments that look like this one. Maybe not exactly like this one, you don't know the map, but you do know that hallways are probably a good way to get to a faraway region of space, and that things like classrooms, offices, and closets are typically dead ends and relatively small in extent. This prior knowledge, this information that you can use to make better decisions, is something that robots typically lack, or at least struggle to make effective use of. So now let's go back and zoom out a little bit to thinking about these more complex meal preparation tasks. Suddenly, this problem of preparing breakfast seems even that much more complicated because what we need to do depends on what objects we think exist in the world and how easy it's going to be to find them. I shouldn't go out and try and prepare eggs if I'm fairly confident that I have run out of eggs, or if I'm, a vegetarian or something like that, right? All of these other common sense or experiential things that determine how I can make good decisions. And unfortunately, or maybe interestingly, and a lot of my work surrounds this idea that effective planning requires nuanced, long horizon reasoning to yield plans that jointly search, interact with objects, and actively gather information about the environment. That's going to be very difficult to incentivize an autonomous system to do. Now, you might be thinking, well, there's been this explosion of machine learning, and in fact, I've probably seen some machine learning-based systems that can do a reasonable job of informing good behavior in these types of contexts. And indeed, learning can help make judgments about what lies in unseen space, about the location of objects that, whose location I may not immediately know or exactly know. And learning, and large language models in particular, can generate reasonable candidate actions. They can sort of prescribe, here's a bunch of things that you might do in order to be able to make progress towards this overall objective. But they can be somewhat unreliable in general and fairly myopic, especially for these more complex long horizon tasks that require the robot to interact with potentially dozens of different objects. So as such, these learned models or foundation models like these LLMs, using them directly for planning frequently results in unreliable or myopic performance, which makes them promising but generally unsuitable for a robot that would operate in someone's home, for which we expect a certain amount of reliability. Instead, I am very interested in leveraging the strengths of both learning to help us make predictions about uncertainty, but also the strengths of planning, sort of classical decision-making, because it is designed around the idea of effective and reliable long horizon decision-making. The challenge here is how to marry these two approaches to get something that can leverage the strengths of both in these sort of open-ended environments where we have fairly complicated tasks that we expect the robots to accomplish. So how do we end up doing this? Well, let's go back to, again, some of the now somewhat older work that I did during my PhD, is going back to think about this point goal navigation case, because I motivated the idea that even point goal navigation is quite tricky, but the insights that we can get from trying to understand how we can more effectively navigate over these long distances in environments that we've never been in before can help us understand how to solve these more general task planning problems. So let's revisit this point goal navigation scenario. In order to try and address this, we introduce an abstraction, some high-level abstraction for navigation, in which the robot's actions correspond to revealing and exploring different regions of unseen space. Indeed, when I originally posed this scenario and said, yeah, let's go navigate this environment, you probably weren't thinking in the same way that robots typically do, which is in the language of trajectories, sort of the like putting my right foot in front of my left and then doing that all the way to the goal. That's typically not how humans tend to think about these sorts of planning problems, especially when the goal is so far away. I'm thinking at some higher level of reasoning or some higher level of abstraction. And in this particular context, the decision that you may have intuited for this problem was, well, do I follow the hallway what I have named action number 2 over here, or do I make this left turn and enter what appears to be a classroom? This action abstraction is something that lets the robot, similar to how humans seem to make decisions, reason more effectively about the long-term, more temporally extended goodness of their actions. And in particular, the thing that we are interested in doing here is not just giving the robot this abstraction and saying, here are the different ways that you can think about acting in this environment. We are also interested in looking at the outcomes associated with those actions. And in this particular case, the outcomes are somewhat probabilistic. They don't tell me whether or not I will deterministically reach the goal. There's some statement about the likelihood of being able to find a path to this goal or towards any of the objects I might be interested in finding by revealing and exploring this portion of space. And framed in this way, it becomes more easy to see how we can encourage the robot to do what humans do naturally. Because by making some predictions based on our experience about the likelihood that the hallway is to lead to the goal versus the unlikelihood of the classroom leading to this faraway goal, the robot can then make more effective decisions about which one of these actions are best, and so avoid these local suboptima, these places that probably aren't very effective for the robot to explore. So what does this actually look like in practice? How do we take this intuition that we think is a good way of representing this problem and imbue the robot with the ability to think in that same way? Well, these exploratory actions correspond to search beyond what we refer to as subgoals, which are themselves just points on each one of these contiguous boundaries between free and unknown space, also often referred to as frontiers in the literature. So in this particular toy sort of abstraction of this environment, the robot has 3 different ways it can leave known space and explore the space beyond while trying to reach the goal. There's 1, 2, 3 different boundaries over here, these 3 frontiers. And the subgoals are just these points on the boundary. So this represents, or each one of these represents an action that the robot can take in this abstracted decision-making model, where the robot can just say, okay, if I want to execute action number 1, I'm going to try and navigate to this boundary and then to the goal. The lower level details of how it actually accomplishes that movement are handled by another lower level processing system, some motion planner that says, how do I actually get my wheels to steer in the right way, to get a trajectory that actually gets me through known space to that boundary, and then continue to replan once I get there, because by the time I'm there, I will have revealed more space and so on and so forth. So it's okay to have this over here. We have some learning that tells us the likelihood that these actions are to lead to the goal. And then I have some way of turning an occupancy representation of the environment that the robot is building as it navigates into these high level actions. How do we actually use this for planning? How do we actually put this into a planning system? Because right now this is kind of a lot of pieces that seem loosely connected. The way to do this is to go back to the Bellman equation. So for many of you, I think, are students, have you seen Markov decision processes? Any of you have? Great, yes, good, awesome. That's what I like to see. So if you've seen a Markov decision process, this is a Markov decision process. This is a Bellman equation instantiated by the abstraction that we use to represent the types of things that the robot can do, its actions, and the outcomes that happen anytime I execute one of those actions. In this particular case, let's break this down step by step. We have the expected cost associated with taking, let's say, action number 1. The first piece of that immediate cost is moving to that boundary, which is actually pretty easy to get because I have a motion planning system. I know the geometry of my robot, and so I plan a trajectory that goes through known space to the boundary. Fortunately for us, this involves no planning under uncertainty. I don't have to reason about unseen space at all. I know how to get there, and I know how to plot that trajectory, and I know its distance. I know how much it's going to cost. However, once we reach that boundary, our abstraction says that one of 2 things can happen at a high level of abstraction. With some probability of success, the robot is able to find passage to the goal and accumulates an expected cost of succeeding. And with the inverse probability, 1 minus this probability of success, it ends up being a dead end. The robot has to turn back around and continue back to known space before eventually picking another action, and the process repeats. It's a Markov decision process, and as you can imagine, the Bellman equation, like most Bellman equations, are defined recursively. The robot envisions recursively expanding this, selecting actions in sequence until eventually it's exhausted all the possibilities. Each time it selects an action, there's some probability that it reaches the goal, and so that part of the tree ends up being completed because it's finished its objective. So this is something that we generally refer to as our learning over subgoals planning abstraction. And the reason for that is because these three terms over here, the probability associated with success and the expected costs associated with successfully reaching the goal and failing to reach the goal and having to turn back and explore, are all estimated from experience via some learned model. So we use learning to make predictions about parts of the environment we cannot see. These estimates of statistics of the belief or statistics of unseen space that then inform classical decision making. This is then sort of in progress towards realizing that promise I said earlier, which is that balance between planning, which is effective for long horizon reasoning, and using learning to help fill in the missing pieces that the planner does not otherwise have access to. So the process of planning with this abstraction is relatively straightforward. Yeah, question. Yeah.
Which of these values, like in the equation, are being predicted and which ones are the ones?
Good. The red underline is for the predicted values. So the motion through known space is not predicted, and then the red is used for pretty much everything else, right? And in the event that actually the world is fully known, I don't actually need to predict anything. I just plan a route to the goal, and I could just get there, right? Yeah, great question. Yeah.
Whenever you have a discrete set of options available to you, there is a risk of oscillating between different options.
Yeah.
Have you seen this show up when implementing this? And
yes, and indeed we have, right? So we add like a small momentum term to try and avoid that sort of switching, a kind of like hysteresis in the code. It actually tends to not happen too often. But in the 1% of cases that it does happen, it ends up being catastrophically bad. So yeah, right. There's a number of sort of empirical little nuances to make this a little bit more stable, because especially since we're predicting these values of the probabilities, what might happen is we move through the environment and the learning itself is a little bit noisy. And so that too can lead to some oscillation. And so having this sort of like time-wise attenuation just for a few steps helps a lot with that, yeah. So practically speaking, there's some other little things that make this work more effectively in some of the extreme cases, but even absent those, this ends up being fairly robust because we're building a map of the environment, we're navigating through it, and it ends up being, it hasn't been a catastrophic problem. Yeah, yeah, great question. Yeah, feel free to raise hands, interrupt, etc. Great. So the process is as you might expect. We compute these actions, we make predictions about unseen space from learning, we plan using the equation on the previous slide, we move towards that boundary, and then as we reveal more unseen space, it is added to our seen space, and the process repeats. We continue to make progress until eventually we have either revealed the map and found that the goal cannot be reached, or we reach our goal. So how does it work? Well, it works pretty well. This ends up being fairly reliable, because we are building a map of the environment, and if we trust our sensors, which again is maybe a dubious value proposition, but as effective as our sensors are for building a map of the environment, we can continue to build the map and make progress towards this goal while learning helps us go away. While learning helps us make progress while avoiding these local suboptima that sort of stymied the optimistic planning approach. And indeed, going back to this larger simulated environment in this other university building from MIT's campus, we can see that the robot generally does a very good job of using learning to avoid these local suboptima and more quickly making progress towards the unseen goal, because it has learned to identify features that associated with actions that are not particularly effective in the short term. So our learning over subgoals planning abstraction has some nice features. The first of those is that this abstraction, this representation, allows us to approximate a very challenging long horizon POMDP, a partially observable Markov decision process, as a far easier stochastic Markov decision process, which could be solved much more quickly and in fact in real time as the robot continues to reveal the environment. Learning is, and I mentioned this a little bit earlier, learning is only used to make predictions about uncertainty. When the world is fully known, learning is not needed at all. This sort of graceful degradation that you might expect of such a system. When I have the map of the world, I should be able to use it for effective decision-making using the tools that have been proven tried and true in robotics for the last 30 years. Planning is also complete, and so is at least to some extent reliable. And I'm looking at Hidaspes. I would like to talk about what reliable means to you after this. But there is an extent to which it's much more reliable than these fully end-to-end learning systems because we are building a map of the world, and actions, these exploratory actions, reveal unseen space, doing so until we fully reveal the map. Yeah.
Wait, so I'm a bit confused, but when the neural network is done,
Yeah.
when it learns,
Right.
Get more information. Do you retrain it on a new space?
I'm glad you asked. Let's wait another 10 or so slides because that was another research project, was deploying these systems and trusting them to do well is dubious, right? What might happen is that if the learning is informing bad predictions, we do sort of arbitrarily poorly when this system is deployed, but we would hope that while deployed, the system can use information it gets to improve itself, and I'm going to get there in a little bit. But the key idea that underpins this work, and in fact a lot of the work that I have done since starting my job at George Mason, is this idea of learning augmented model-based planning, where learning is used to make some predictions about things that the robot otherwise doesn't have access to. So in this case, statistics of uncertainty that define the parameters of a model, which is then used for some classical planning or decision-making, without any reliance on learning. And so this is some work then, I'm looking at Hadas because Hadas is a co-author on this paper. So back in, it was 2001 when I had just started my job. Co-authors Chris Bradley and right. 2021, yes. No. Yes, good. Yes, thank you. Yes, no, just a handful of years ago, but it feels like a lifetime. But Chris Bradley and Adam both worked on this idea of trying to extend this idea to think more generally about beyond goal-directed navigation, where exploratory actions for solving something like this abstracted putting out the fire scenario, expressed in the language of linear temporal logic, the exploratory actions were there to say, well, I can leave known space, and rather than just trying to find a goal that I'm interested in reaching, now I'm looking for any of a handful of objects that I may need in order to be able to advance my progress in terms of satisfying the specification, so advance the state in the DFA that represents this scenario. And then meanwhile, the robot also has a bunch of known space actions. If it already knows where the fire extinguisher is, it doesn't necessarily need to look for another one. It can, but can also take an action within known space to interact with the entities that are already observed by the robot. And so we actually saw quite a lot of success with this, and we've continued in my lab to build on some of these other ideas and some new stuff that I'm going to gloss over really quick because despite the fact that I'm talking really fast, I'm still behind time. Is we've been thinking about this as well in the context of PDDL, where this planning domain definition language, which just flummoxed by the fact that it doesn't know where the mug is in this particular coffee preparation inspired scenario. If it doesn't know where the mug is, it says, nope, can't find a plan because the mug does not exist. There's some possible solutions to this. Kind of look around and search until you have enough objects to complete the plan. And there was some good work from George Kennadaris and his lab and his student Max Merlin, both of whom were actually collaborators on this particular project, that does just that. Let's continue to map the world until we find all the objects that we need to complete the plan and then complete the plan. However, that's not very cost effective. Certainly humans don't need to do that. I don't need to map the entire environment before I can start making decisions or start acting. And in fact, the idea is that using some of these learning over sub-goals planning ideas, we can use learning to help find objects more effectively. And there's a pretty simple plug and play with this idea where we can augment PDDL, just kind of off-the-shelf code that you might get to represent a task planning scenario, like find a bunch of objects or prepare coffee in this home environment. Add a find operator that says, well, let's just give PDDL the ability to find an object that it thinks it may need. And by just adding this find operator, PDDL can now return a plan where sometimes it knows that it may need to find an object in order to complete its task. And so in the process of going from this counter to the table, it is expected to find the mug, however it deems appropriate. And indeed, we can instantiate this find operator, this find action, using our learning over subgoals planning approach, because it's a learning augmented approach to finding an object. It's going to try and sequence how it needs to look around the environment to try and find that object relatively quickly. So this already represents something of an advance on the state of the art, because we can use very nearly off-the-shelf specifications for acting in a home environment, but augment it in such a way that we can now make good decisions even when the objects are missing. Because whenever it deems that an object it needs is not found, it knows that it needs to look for it and can do so effectively, informed by learning. The problem here is that it doesn't necessarily know which objects it needs to look for, and maybe more importantly, when to look for them. The fact that this find action happens at a convenient time, when it passes nearby the shelves on which the mug is located, is not a coincidence. And in fact, the key here is actually connecting that high-level decision-making that knows when to find objects and which objects to look for with our approach to actually effectively searching for those objects. And so this is very new and I'm still honing it and I'm happy to talk about it. I can send people the manuscript if they're interested. But the idea here is that we are not merely instantiating these find actions with an effective search policy. Our model-based approach to learning-informed search means that we can also determine the expected cost associated with finding an object and when we look for it, which is then used to instantiate the PDDL code so that at the high level, the system can judge when and where to best look for those objects in the course of doing its business. This idea that planning interleaves search and execution is a big deal and something I think about a lot. I shouldn't have to take a phase of my execution to look for stuff before I start making progress towards my objective. And this brings us one step closer to that vision, where the robot is then balancing both doing parts of the task, starting to like, grinding the coffee beans and then looking for the mug because it's nearby, all during its execution. And so we have this like monolithic system that I'm really excited about, and we're going to release an open source tool soon that says you can do PDDL and effectively, even when many of the objects are missing. If that was kind of a whirlwind tour, that's because it was a whirlwind tour. We just finished this, and so I was really excited to talk about it. But the bottom line is the results are really good, and I'm happy to talk about them offline if people are interested. So with that, there's a number of different applications that we have achieved using this same general philosophy, this idea that we're balancing planning and learning, or we're using the best of planning and learning to complement one another to achieve these systems that have, at least to a certain extent, some amount of reliability or completeness guarantees up to what our sensors are able to guarantee, while also allowing good performance in these complicated open-ended domains. We've managed to do things like coverage maximizing exploration. So, how can we very quickly and effectively navigate or reveal as much of a map on some limited battery life. We've also done some things, and I'm really excited. We just got awarded this big Army Research Lab grant to work on some of this stuff, or at least this is a component of like a 4-faculty grant for which I'm the PI, but some multi-robot coordination as well. We can take the same abstraction that we use to talk about how a single robot can make good decisions in these environments, and then use them to say, well, here's how a multi-robot team can split up and collectively be making progress towards multiple objectives simultaneously, revealing different parts of the environment, trying to accomplish different pieces of a task all at once, all built on this same underlying abstraction, and then using learning to inform which actions the robot can take are particularly effective. And then one thing that perhaps you have been wondering about is, well, how are you actually doing this learning? And I've swept that under the rug for a good reason, is because our approach segments what learning is used for from what planning is doing, which allows us to be fairly agnostic to the choice of learned model that we use to make these predictions about unseen space. And as a result, we've done pretty much everything from images and thinking about convolutional neural nets, from panoramic images to make predictions from cameras, like like you did when I showed you this picture of the university environment, to using graph neural nets and graph representations of an entire map of the environment all at once. And then, of course, jumping on the large language model hype train and describing the environment to the system, and then having it make good predictions, allowing it to look for open-ended objects, despite just using the sort of magic and witchcraft that is ChatGPT. So this is new. I think it's effective. It's not particularly interesting to me, but I'm happy to talk about it if people are interested. It's just another way of making these predictions. And I think it's interesting in the sort of flexibility that it affords, not the fact that it changes the nature of the way we actually do decision making. Now, so far, and this is to the comment from before, so far we've made an assumption that the environments that we see at test time are similar somehow, right? That I train in some set of environments and I deploy in environments that have similar underlying characteristics. However, during deployment, that may or may not be a good assumption. And the reality is it's very difficult to judge in advance, or even when we are deployed, if that assumption is met. It's very difficult to look at a new map and say, yep, this is fundamentally different in some way that would lead to poor behavior when the robot is deployed. But as you can see from this particular example in these sort of maze-like environments, the robot can perform almost arbitrarily badly before eventually going and finding the goal, right? And this isn't great because I don't want to just train these systems offline, or in the case of ChatGPT, do some prompt engineering offline, and then assume that that's the right prompt for all systems or the right training data for all systems, so that when I deploy these systems, I then just trust that that's going to do well and wish my robot luck. It's not very user-friendly, and it's not very effective, and it's certainly not what we as humans do. So let's instead imagine that rather than being deployed with a single learned model or some single predictive model that lets it judge what might exist in unseen space. The robot now has an ensemble of models, each one trained in a different type of environment. So you can imagine one's trained indoors, outdoors, hospitals, university buildings, my house, your house, etc. And then each one of those could be used when the robot is deployed to inform its predictive model and so inform its behavior. Each one of these policies is using our learning over sub-goals planning approach, but the underlying learned model is trained using potentially vastly different data. And over here I have some images of a number of different simulated environments, all with different lighting conditions and colors, in fact, geometry, although it's difficult to see just from the panorama, so that each one of these will perform very, very differently in each other environment. Does that make sense? Great. So when deployed, the robot, and even I, probably won't know which of these policies will perform best. The goal here is a model selection problem, or just like a streaming selection problem. So I imagine people are pretty familiar with upper confidence bound bandits. If you've seen markup decision process, you've probably seen bandit algorithms and things. The idea is, let's use a multi-arm bandit. Let's just try them one at a time. We'll deploy, we'll be put in a new environment. We'll pick one of these policies, perhaps at random at first, but then using some more intelligent selection process as time goes on, to pick the one that we think is going to perform best. And then we do this over and over again until we converge on the one that actually does perform best. So people okay with the setup? We're going to just try them, because in the absence of external information, there's not much else I can do. I just have to try these a bunch of times and then eventually figure out which one is best. The upper confidence bound bandit is the classic exploration versus exploitation selection strategy. We exploit on one hand, we pick the one that does best based on our data so far, versus exploring to try and pick approaches that may not necessarily have been best so far, but show promise for potentially improving performance in the aggregate. However, this black box approach to model selection can be problematically slow to converge. Remember, each one of these bandit pulls, which in the multi-arm bandit case is like a slot machine, is not just a matter of pulling a lever and waiting for a payout. This is an entire deployment in a building scale environment. And as a result, taking many deployments to converge, or many different trials to converge, is not great. Excuse me. Excuse me. So this blue curve over here represents the expected payout averaged over, this is the empirically computed payout over many, many runs. And this orange line represents the oracle, the thing that we know after the fact to be the best performing strategy. And even after 100 trials, we're still fairly far away from converging to the best performing of the 6 strategies used in these relatively small scale maze-like environments. Excuse me. So that's not great, because that's a lot of time. That's 100 deployments, each one of them a navigation from point A to point B. And for those of you who work on ground robots, how many of you think you've done 100 deployments total? It's a lot. 100 is a lot, so that's not great. However, information that we use during navigation can be used to inform selection. The idea that we have here is to then go back to not just treating this as some black box system, but to leverage the fact that our learning over sub-goals planning approach says, hey, I actually can have an approximate model of what decision-making looks like in this environment. And so ask myself counterfactual questions about the behavior of the agent if another policy had instead been deployed. So let's look at an example, because that's kind of like a lot of words all at once. Here's an actual deployment. I deploy policy pi deploy. Here's a top-down version or a top-down view of this maze environment. This pi deploy policy correctly understands that in this environment, the green path on the ground is a visual signal of the route to the goal. So even when it doesn't have a map to the goal, it follows the green path, it gets to the goal, does really well. Excuse me. The question that we then want to ask ourselves in a computational way is, how would my performance have changed if I picked another policy that at this fork in the road wanted to go right? Now, you and I can see, based on this, even though I don't know what lies in these parts of the environment over here, that would have been worse. This deployed policy did very well, and in fact has the best performing strategy. And so any deviation from this behavior would have resulted in poor performance. Excuse me, there it is again. So some policy pi alt at this fork in the road insists that going to the right is the best thing to do. So what happens to the performance is that it goes down. Now, I can't tell you exactly how much worse this performance would have been, but I can put a bound on how much worse it would have been, because this policy would have tried to explore here and then here before eventually returning and following that green path to get to the goal. Even though I don't know exactly how much worse it would have been, this information can be used to constrain selection and say pi alt could not possibly have improved performance, and so I shouldn't go out of my way to select it in this multi-armed bandit-like approach. Excuse me. The idea here is to compute lower bounds on cost to constrain bandit-like selection. This is at the foundation of what we refer to as offline alt policy replay. No, the name isn't perfect. No, it was not this originally, but after like 3 reviews, this is what it is. So the idea is that we use data collected during deployment to instantiate a simulator. We can imagine what the robot would have done had it been deployed in that same environment, but using a different policy to inform its decision-making. And the resulting trajectories then form a lower bound on the cost of those alternate policies, a constraint on bandit-like model selection, which allows us to select much more quickly. Yeah.
So can you go back to the slide?
Yes.
Here. So the reason that we can like imagine like the other alternate policy can perform worse is because we as humans, we like kind of automatically compute the value function at each state.
Right.
By looking at the thing. But the problem is, take your time. Sorry.
Yeah. No, this is, keep asking. This is great.
Yes. So the problem is during deployment, the data I see is only on the support, like the data support that I collected.
Yes.
Only contains the states that I visited.
Yes.
So I can like, how are you gonna actually compute the lower bound?
This is a great question. And we asked ourselves this very thing when motivating this research. So the thing that we originally did was what we were interested in was like looking at these points at which 2 policies disagree and sort of try and estimate how bad those are and then sum them all up. That doesn't work because as soon as you start actually navigating, you end up off policy, which is kind of what you're asking, right? Is you end up being in a scenario that the robot hasn't been in before. But the thing about our learning over subgoals planning abstraction, this abstraction that I've motivated for much of the talk so far, is that we have abstracted away a lot of that level detail. And we can still instantiate that approximate, though imperfect, model that says, what would a robot do if placed in this scenario where it's here, it knows it can go here, here, or here in order to try and explore. And these are pictures of what those parts of the environment look like. And so we can make those predictions, right? We can do as much as we want within the space that the robot has actually mapped out. The problem is I don't know what it does over there. But in this particular case, in fact, this happens fairly often, I know that this could not have improved my performance because there's no other route to the goal. In fact, if there had been not a dead end over here, it's possible that this could have achieved very similar performance to the original plan. And in that case, there's sort of no loss here. We're trying to compute a lower bound. It ends up not being a very tight lower bound on performance. And so the worst case scenario here is that we imagine what another policy might have done, and the performance ends up being maybe better, in which case our multi-armed bandit should select it. This is here, this approach of computing these lower bounds is there to rule out policies that could not possibly have improved performance. And so there's only benefit here. Right? But I mean, it's a great question, right? In the worst case, in fact, in some of the cases where we deploy, we see no benefit from doing this over the vanilla approach. But as long as we are confident that our abstraction is a reasonable approximation of reality, which empirically we've shown is a pretty good approximation, this ends up being very effective.
So the assumption is like you, at the fork, you already see that there's a dead end.
Yeah.
At the other side.
The fork is... No, well, yeah, right. So actually the thing that we do is we actually simulate the robot going all the way up to this. And then as soon as it leaves known space, we say, there would have been a dead end here because there's no other way to reach the goal more quickly. And we like force the system back. We just don't allow it to pick this action anymore.
I see.
Yeah.
How do you know there's
Yeah.
no corridor in the middle?
We don't. And in fact, right.
We've gone to that area and then be direct.
yes. So this is an example that shows the like best case scenario. In the case that you're describing, there's no benefit, but also no harm. So we allow the robot to imagine leaving known space. And if there could have been a shorter scenario, we allow that too. Sorry. We allow that to happen. So in that particular case, it goes here and then says, oh yeah, look, there could have been a shortcut to the goal. In which case the like lower bound on cost is actually really low and doesn't constrain selection at all. That makes some sense. If there was a shortcut, we allow the robot to imagine taking that shortcut. It just doesn't actually, the value of using this approach to imagine doesn't actually add much information.
And this is after the robot made it to the goal that you kind of.
Yes, so we do this. So we do this whole trial, and then after one trial, we imagine all the other policies.
Then you already made it to the goal. So the purpose of that is what?
You're doing this over and over again, right? It's very difficult in one trial to gain enough information to judge that your policy is the right policy. This is like a distributional question, because even that would be incredibly biased. Makes sense? Sorry, so in this particular case, sorry, I'll call it just in a bit, this is 100 deployments over here, right? So you've now seen that one image is just one of those, right?
But your task is to get to the goal.
The task is to get to the goal, but the meta task is to learn how to get to the goal or figure out which of these policies gets to the goal more effectively in these environments that you are now deployed in.
This specific environment, not
In these distribution of environments that you're now deployed in. There's a bit of a wishy-washy, like, what does it mean to be in a distribution environment? We have maybe a slightly more realistic case now where we're thinking about homes, and we can redeploy the robot in the same home over and over again, but by giving it different objects to look for. It needs to learn the sort of patterns associated with this user. That's slightly more realistic. Yeah, this is a good question. Yeah.
Can you go back this slide?
Yes. Oh, no, you mean front to slide because I jumped around a lot. Yes,
Yes.
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 This one, yeah.
When you are making the underestimate of the additional cost.
Yeah.
In this case, it seems pretty simple because you can just use distance as a heuristic. Am I understanding that correctly?
Yes, yeah, that's correct.
Okay. How well does that approach perform when you don't have a clear heuristic for what the cost might be?
Good question. I mean, so I will say that I think I've circumvented this issue in most of my work, where I assume that given information about the environment, I can then imagine what would happen if I were to then again deploy the robot in that environment. And so I think like, I'm thinking very much about, I know what this part of the map looks like. A colleague of mine, Shuisu Zhao, thinks a lot about like off-road navigation, that even seeing some part of the environment does not tell you for certainty whether it's muddy. And in that case, I think it would be hard, right? There becomes this chicken and egg problem if you want to use something like learning or a model that you don't necessarily trust to make predictions about what other parts of the environment look like, and then rely on those to tell you how good your model is. Because then you end up with this feedback mechanism, and you then have to have this sort of abstract notion of how much you trust any of those models. This approach sort of assumes, yes, that when I've seen some part of the environment, I know as much as I could ever need to know about that environment. And that I make as minimal assumption as possible about what information I need, about the goodness of any of my policies. There's a sense in which I don't make any assumptions about how good any of these predictive models are until I am deployed, which in practice is not a very good one. And so we're thinking about, we can very easily relax that assumption, but where do you draw the line? And so, it's like, I think if I were to physically put the system on an actual robot that was like a product and not more of an academic exercise, I would be very interested in thinking about how to fine tune those things and how to get the most out of my performance. I think that ties a little bit more into what you're saying is, I'm trying to make as minimal assumptions about the environment as possible. Does that make sense? I know it's an unsatisfying answer. The answer is no, I think. Does that make sense?
Yeah.
Great. Anyone else? Great. I want to be mindful of time. Yes.
Maybe I'll just make this one
No
quick.
worries, yeah.
So it seems like this method is very based on, like the efficiency is based on
Yeah.
how effective your first model is, or the first policy you choose is.
Well, no, because we're still picking a handful of these policies. So I think that's true. Is, you pick one of those policies and then, for the very first time, you really are, it's just luck. right? But the next time with a just black box bandit algorithm, you'd have to pick another policy at random. But in this particular case, you don't need to do that at all. And in fact, what happens in our approach is we don't even need to deploy many of the policies because we can already imagine them and know that they're not it's not possible that they could have improved performance. And so even as you scale up and up and up in terms of number of policies, you can converge fairly quickly because you can just rule out the poor performing ones fairly quickly and then do your sort of multi-arm bandit with the policies that kind of remain. It's a simplification because there's like good math that shows that this is still asymptotically optimal with sublinear regret, which is the property that you would want out of a bandit, but empirically converges way more quickly, right? Just do much more quickly rule out those poor performing policies. So that's this approach. I'm done at 2:40, is that correct? Great. I'd like to jump ahead ever so slightly. I think there's one final thing that I'd like to talk about because it's a really cool idea. And unfortunately, Tom Silver had to go, but he's a co-author on some of this work. So far, I've mostly talked about uncertainty in space, but I'm also really interested in this idea of uncertainty over the future. That even when I know what my environment looks like now, there are things about the future that determine how effective my behavior is that I can't know about in advance. And so the same ideas that we have about making predictions about the goodness of our actions with respect to parts of the environment we cannot see hold also for parts of the future that we do not know in advance. And so let's revisit this simple scenario, seemingly simple scenario, where we want to load a bunch of objects into a cabinet. So I take a bunch of objects and I load them into the cabinet. Is this good or bad? Okay, continuously valued thumbs up. I want to see. Who thinks that this is good or bad, right? Did it accomplish the task? Yes. Why are some of you uneasy? Yeah.
It probably didn't satisfy a user's preference.
Right, so there's some preferences. I'm interested in this too because I think there's some really cool work and I'd love to talk about preferences, but some of it too is even in the absence of thinking about what a user prefers, there's some amount of what the user does next is then influenced by what, how well you did this. So if I ask you to then remove the bowls from this, I have to move the mugs out of the way. There's a way in which preferences like sort of tidiness and organization capture this, but from a purely cost-based perspective, if there's another task I need to do next, even if I don't necessarily know what it is, but I have, let's say, a distribution over future tasks, I can show you that this is not as good as this. Because now if I am tasked to unload one or multiple different types of objects from the cabinet, I could do so very easily. And so even though it's slightly more expensive to put the environment in this state, the total expected cost ends up being less. This is the sort of motivation behind what we refer to as anticipatory task and motion planning, where our anticipatory task and motion planning solver tries to estimate the expected future cost associated with completing a task in a certain way, basically leaving the environment in this state. We use learning to try and estimate that value from data that we can collect offline. And then when we're doing planning, we use that as a search heuristic. So that when we're trying to load the objects into the cabinet, we're constantly asking ourselves if the environment that we are building by, in solving this task is doing so in a way that respects the needs of the uncertain future. And so that's a really high level overview because I have like 2 minutes left. But the short version is we do the thing. We accomplish that goal. One thing that I think is really interesting as well is preparation, which is zero task anticipatory planning. Even in the absence of a task, we can ask the robot to put the world in a state that is organized or prepared or minimizes expected future cost. And what happens is the initial task becomes much cheaper. By continuing to think in this way, by continuing to ask ourselves, are we paying down expected future cost? We can keep the task cost low over multiple tasks. Giving the robots 10 tasks in a row. And unlike many robot experiments, not resetting the environment between tasks. However, if we allow the robots to prepare first and then myopically solve tasks, the environment tends towards entropy. And over time, the cabinet will become disorganized because it doesn't have an appreciation for how that messy, unorganized cabinet leads to worse and worse cost over time. So that's most of what I have. I'm really interested in this idea of anticipatory planning. It's like an emerging new research direction in my lab. And I think there's a lot of potential here to think about preferences, like what gives rise to these sorts of preferences. There are more cost-based formulations for this. I'm really excited to talk about this. So if anyone wants to talk today or another time, please do send me a message. But the short version of all of my kind of overview is a lot of the advances in my lab are made possible through this integration of planning and learning. Use planning to do what you know how to do, to change the state of the environment, et cetera, but use learning to make predictions about statistics of the environment that you have difficulty accessing directly. Don't replace learning with planning, augment planning with learning. And so generally speaking, I have a lot of code. Please check out our code. Let me know, issue pull requests if there are bugs, but there shouldn't be because we have a continuous integration system. Happy to talk about that too. But anyway, with that, I will be respectful of your time as best I can, and I can take any additional questions as you have them. Thanks so much, everybody. I do know we're out of time, but I will be here for at least another 20 minutes. So
Awesome. Maybe officially, maybe time for one question, and then of course, Greg is here.
I think I got all the questions.
So,
Yeah.
so in a lot of your talk, the formulation is that you want to learn things that you don't know about, and I think it's mostly related to perception of the environment, if at a broad level. A lot of the learning you're doing is trying to optimize the perception performance or knowing about the world. It's not really reasoning about the perception that will help you with planning. Have you ever thought about that? Like, how do you optimize your perception towards planning?
I have a paper that I'm really proud of that has not gained much traction, but I'm happy to talk to you about, that I had to skip over because of time constraints, et cetera, on active information gathering. This is a scenario, there's a scene in Die Hard, I love Die Hard, but when Bruce Willis is like running away from some bad guys through a construction zone, and he stops, which is like, oh my God, run away, to tear a fire escape map off the wall, right? Now he has a map of this building that he's unfamiliar with. This is the robot equivalent of that. The robot goes out of its way to seek out a map of the environment because it understands, it can predict the expected value of having been given that information. So this is something I'm very interested in. I think, you can't talk about planning under uncertainty without some amount of information gain. Short answer is yes, I'm very interested in it. Message me about it. This paper was at IROS, I think. I don't know, it got rejected like twice, but I think IROS is where it ended up.
Thanks.
Awesome. Let's thank Greg again.